Yes, okay, now you can hear me. Welcome to the World Soil Museum of ISRIC World Soil Information. My name is Stephan Mantel. I work for ISRIC and I'm leading the activities in and for the museum, including the physical collections of the museum. And let me show you, well, let's go to the introduction wall. There you see that we really are in the World Soil Museum. And I would like to take you first to a place in the museum. Let me turn the camera. Just a moment, please. Yes. So here in the museum, we have some minerals here in the museum. And I have them here. Well, there are an enormous amount of minerals that you could display, but the minerals here in this cabinet are all the result of soil formative processes. And like hardened layers of calcium carbonate, gypsum, different forms of calcium carbonate, iron, also like bauxite, petroplintite. So this shows that soil forming facts are quite strong, but they take place over long periods of time, and they ultimately result in different components leaving or entering the top part of the earth crust. And I start with that because ultimately, the soil forming processes are the basis of our whole collection, actually. And the World Soil Museum, the World Soil Museum is a display for soils from around the world. So we have a large collection that was gathered from 1966 onwards till today. So 1966 was the foundation of our institute. And we have, over that time, we have visited 1,200 sites in the world in about 85 countries where good representative soils, according to the legend of the soil map of the world, were sampled, described, and we collected monoliths from them. Monoliths are 3D, let's say, real samples of soil taken from a soil wall, which is actually our primary collection. And here in the museum, we show a selection of those soils. So we don't have all the 1,200 monoliths on the wall. We show 90 to 100 here in the museum. And of course, they are good representatives of the major groupings that you find in the international classification systems, especially the World Reference Base for Soil Resources. And what we do here in the museum, well, it's of course, the collection by itself is a scientific reference. It's the only worldwide collection of soils gathered for that purpose, for science and education. And also, so the people that come to the museum, which are mostly student groups, higher education groups, but also other general groups, primary schools, secondary schools, general interest groups, we try to explain soils, of course, and to be an advocate for the importance of soils, and to put soils in the context of the importance, ecology, but also society. And soils are all around us. Everybody experiences soils every day, and most of the materials that we use are indirectly or directly related to soils. And yet soil is a difficult subject to explain because everybody can relate to sand and silt, knows what that is. But then going one step further, understanding that soils are variable, on short range, but also over landscapes, over continents, over the globe, and with depth. That is something that is not taught at schools. There's no museum to visit. In natural history museums, soils is rarely represented. It's not in textbooks, so at least not for general public. So how do we expect that people understand soils? And that's what we tried, at least to have a small contribution here from the World Soil Museum to make people aware of soils and the importance of soils. So, well, about the setup of the museum, the 100 profiles here include, of course, the 32 reference soil groups from the WRB as a representation of the World Soil Map. But then you have to think about, or at least we had to think about, how to show those soils in an interesting but also logical way in the museum. And well, we thought about showing them by the continents or by biomes like the rainforest and the deserts, but ultimately we decided to show them by their dominant soil forming factors. Most soils have multiple soil forming factors under the influence of which they have formed, but you could, for many soils, identify what is their major soil forming factor. So we have on the wall, I'm going.
We don't hear you anymore.
Stephan, we don't hear you.
Okay, do you hear me again? Yes.
Yes.
Was I muted for a long time? Okay, so I just repeat, because I was muted, that the division in the museum, the soils are organized by the dominant soil forming factor that explains their properties. So the climate, the landscape, if they are from the sloping lands or the valley floors, the parent material, because obviously the source material of the earth crust in which soils form can have a bearing, or has a bearing, on the properties that will ultimately be shown by the soils. Organisms, the mixing of mineral with organic material, the engine for soil formation, and then time, because soils continue to change over time under the influence of the other factors. So that's the structure of the museum and how we show soils, the collection on the wall. Yes, sorry. Now I'm trying to turn the camera. Yes. So let me show you the soils here in the museum and take you in a journey along the soils of the world. And in the process, I will also explain you a bit the principles of the International Soil Classification, WRB, because this week you've been working a lot with data and models and spatial representation, and but classification is ultimately also a way to group the complexity of the soils that we see around us, that we can describe, using properties that we describe and can observe, measure in the field and in the laboratory, and then making a sense of that in terms of what is similar and what should be grouped in other groups in the classification system, and using that as a framework for knowledge. Now, in most classification systems, the first question is, are soils mineral or organic? And well, this is in the Netherlands, we have a lot of organic soils. This is an example of an organic soil. It's a histosol, so a peat soil, and you see that it has quite a bit of organic material. And in WRB, that's a diagnostic feature, organic material, which means material with more than equal to or more than 20% of carbon. Now, organic soils are quite particular. Peat soils, they are very particular in their properties. They are very light. They have a light bulk density. They have a capacity. They are mostly pore filled spaces. Let me put the light on the peat soil. And in WRB, it works in a way that you work with diagnostics. So you have to have a certain feature, which has to meet certain criteria, a threshold, like in the case of the organic material for the peat soils. It has to have a minimum of 20% of carbon. It has to occur at a certain depth mostly, and has to have a certain thickness, like the organic layer with organic material should occur within a depth range and with a certain thickness. If we have 1 millimeter of peat or 1 centimeter of peat in an overall mineral soil, then it doesn't express the properties of the soil enough to relate to peat. So that's for most diagnostics in WRB, the expression, the thickness, and the depth of occurrence. And then there are fixed criteria for that to identify it and let it be within that diagnostic and ultimately in a reference soil group, yes or no. Now, in the Netherlands, we have quite a few of peat soils in the coastal, behind the dunes, in the central part and the western part of the Netherlands, but also in the eastern part. And we have drained, well, first excavated for making peat bricks in the times when we used that to heat the houses and stoves. And after that, usually areas became so wet because of the excavation of peat and flooded. So then people decided to empolder them, to drain the areas, and then that could be used for agriculture. So that's a big management intervention in the Dutch landscape. The issue with that is that if you drain peat, the water-filled pores spaces will be emptied, and you get land level decline. Not only because of that, but also because the peat will decompose in reaction with oxygen. So that is not a great feature if you are already in the lowlands. Our land is getting lower in those parts. And also CO2 is escaping to the air. So that's really a policy and landscape management, land planning management issue to consider in Dutch policy. And that's really addressed in policy nowadays. But we have to deal with different stakeholders with different objectives. So there's a big debate about this. Okay, then in the river plain, let me turn the camera again. In the river plain, we have poorly drained and some moderately well to well-drained soils like these two. And you see the poorly drained soils are the soils of the back swamps, which are a bit further away from the river, heavier clay, water standing in the profile, high groundwater level. And then you get these grayish colors from reduced iron, heavy clay structural elements, like even a kind of slick inside here. So water high up in the profile. And mostly these soils are used for grassland. So we have a lot of milk production in the Netherlands, milk and meat production, and they are mostly on these soils. You have variation in the river plain, like soils close to the river of the levee, where much of the medium to coarser sized material is deposited, because that can settle even when the water is turbulent. And then you get soils a bit higher up in the landscape, and therefore the groundwater level is deeper. Therefore, more oxygen into the system. And what we see here, because these sediments are high in calcium, calcium carbonate rich, which means a rich substrate, which is a good environment for worms and other biota. And we see that here from this soil. We see worms going down to deeper than 1 meter, really having a party in this soil. And mixing very intensively the mineral with the organic material. And you see that roots are following, lazy roots are following the worm holes going down with least pressure to penetrate into the soil. And so this soil is highly bioturbated and higher in organic carbon content because of it, and very fertile soils, among the best soils in the Netherlands. So you find all kinds of different land uses on that. Now, when I was in primary school, we were proud of our newly added province to the Netherlands, which is the Flevopolder. And the Flevopolder is our 12th province in the Netherlands, which is completely reclaimed from the sea. And this is the soil from the Flevopolder or a similar area. So we see here a soil with shells in the subsoil, in the shallow subsoil. We see oxymorphic features, so reduction and oxidation of iron because of the influence of groundwater. And this is mostly just sedimentary. But then if we go up in the profile, we already see the formation of larger structural elements. So the formation of structure and also color differentiation, because the soil is more darker in the top. And that is because of the introduction of worms into the soil after the reclamation, gluing together the loose clay particles to soil pads. And well, so you see that soil formation can advance quite fast, but it needs time. And actually the Flevopolder is our most productive agricultural area. So those are relatively young soils, and we call them Canby soils in the WRB system. So soils with already signs of soil formation, but not yet to the extent that they're so diagnostic for other more expressed features to group them in other soils. So young soils with a cambic horizon, so showing color differentiation and structure formation. Now, if we look at, so I'm talking about the soils of the Netherlands, and if we look at the soil map of the Netherlands, this is a very crude representation of the soil map of the Netherlands. The soil map of the Netherlands is 1 to 10,000 in most places, and overall 1 to 50,000, a database publicly available. And we see the larger variation here. We see the sea clays, the swamps with peat soils, and here there are also peat soils. And then we have the coastal dunes. And here we have these lighter features are all related to the ice ages. And so there was the ice age before last we had a glacier intruding in the landscape here, ending here with ice-pushed ridges. And then in the last ice age, there was no glacier in the Netherlands, but we had a polar desert and the North Sea bed was dry. And then wind blew material from the North Sea bed to the east, this way, to the east. And cover sands were deposited here. So poor material, silica-rich material, and we had mostly swamps here. And I recently did a study with my colleagues in Wageningen University Research in a project that studied, we mapped marginal lands for Europe. And well, we made criteria and then used all the information layers like the soil maps and the climate, etc. And then we had an overall map of marginal lands. And then we looked at the map of the Netherlands and we said, this can't be right because the Netherlands was dominantly marginal. And the Netherlands is the second largest producer of agricultural products. And 6% of all agricultural products traded in the world originate from the Netherlands. And the first producer in the highest producer of agricultural products is the United States. And they contribute 9% to all traded products. But the United States uses 364 million hectares for that, and the Netherlands 2.2 million hectares. So very productive, and well, then we can't get away with a map that shows the Netherlands all marginal. But then we realized we had to overlay management because something has been done to overcome these limitations. And so the sandy areas are all fertilized already before mineral fertilizer by using organic material and manure. And now with cattle production, the manure is going to the sandy areas. And the river plains and the swampy areas, of course, the management handle there is drainage. So we have a lot of polders, a lot of drained areas to overcome this limitation of lack of oxygen for roots for growing crops. So yeah, so that is a nice example of natural conditions and the influence of man. And I'll come back to that on some of the soils here. Well, let's start. Let's continue with this with these man-influenced soils. One of the archetypal soils in our systems is the pot soil. The pot soil is a wonderful soil, just because it's beautiful and it has such particular features. And a pot soil is usually found in temperate areas or in mountain areas and under acid vegetation, so heathland vegetation, pine trees, on a silica-rich sediments. And then you see that the topsoil is leached because of the acids of the vegetation, the litter layer and the roots affects the minerals, and whatever is there that can be chemically affected will leach down and then precipitate in this spotted B horizon. So that here, under a pH change, we find accumulation of iron, aluminum, and organic matter components. And then this is the leaching zone. And on top, you see the organic material, the litter layer, which is not mixed with the mineral layer as in the other soil. And that is because this is a very poor environment for biota. So it remains on the surface. And this layer will ultimately thicken and deepen as soil formation progresses. But you can imagine that this is a very, very poor substrate for farming. And people survived on these soils in former areas, in former times, by using an integrated farming system, using cattle to free-ranged on the heathlands, and then they were kept in the stable at night where it released the dung, and the farmers families were cutting with spades the heathland vegetation, bring that into the stable, and that mixture of vegetation and manure was brought onto the land to improve the soil quality so that they could produce crops to survive. That resulted in man-made topsoils, as you see here. So this is the original soil, and this is the soil changed from that. And you see 1/2 meter of man-made topsoil on the left. And that is the result of long-term addition of a mix, organic material mix, most of which we decompose and go into the air as CO2, but a part would remain as residual and then build up over time. And in many cases, these fields are a bit higher up in the landscape because of the long-term additions. So that is an anthropogenic soil, an anthrosol. So they are classified separately in the WRB. The man-made top layer has to be 1/2 meter at least. Then it is called an anthrosol, and the system by which this is created is called, it's a Dutch word, it's called the pluggen system. So there's a specific qualifier for that to identify the soils that originate from that system, and it's called plagic anthrosol. Now, so that's again an indication that you need a certain feature, the plagic horizon, which needs to have proof of anthropogenic origin, like artifacts. It has to have a certain thickness, 1/2 meter. But what if it doesn't reach that 1/2 meter? Then you still call it plagic. You can still apply the qualifier, but then you have to call it by its original name, the potsol. So it's then a plagic potsol. So say it's 30 centimeter. If it's 50, then you call it a plagic anthrosol. So then we are at the man-made soils, and we have a separate section for that. In the clogged formula, man is identified under organisms. Well, we cannot go against that. We are an organism, but there are discussions that we should add an additional factor, man as a soil forming factor. And here we have examples of soils that are either deeply influenced or almost all man-made. So let's have a look at them. One of the first soils I would like to see here, that is a mysterious and very interesting soil, is the terra preta soil. So those are soils that occur in Brazil mostly, and that occur in the Amazon. And they were described, there was mention in literature of black soils in the Amazon. And black soils, you don't expect that much in intensive climates like in the tropics. I talk about mineral soils. And here on the panel, we have Dr. Sombroek. Dr. Sombroek was the second director of ISRIC, and he was the first to describe terra preta in scientific literature. And he wrote his PhD thesis when he was a young man, which is called The Soils of the Amazon. And his whole life was by and large dedicated, among other things, to the terra preta. And he was a big advocate of doing research on that. And because the mysterious thing is that these soils, we know these soils were created by pre-Columbian indigenous populations, and most of them which disappeared after the advent of the Europeans to the South Americas, because well, multiple factors. One of them is that they brought diseases to which the indigenous people had no resistance to. So this system more or less suddenly stopped over 500 years ago. But after 500 years, these soils are still black, pitch black. And the blackness of a topsoil and organic matter content in the subsoil is an equilibrium between input and breakdown. And if the system stops, which we know that the indigenous populations added a lot of organic material, charcoal, fish bones, adding phosphate, and those kind of things, it stopped. And then you would expect that after 500 years, these soils would have gone back to their natural state because the breakdown continues, but the input stops. But they remain black. And that is very interesting. That proves that these soils have been made long-term, sustainably fertile from the poorest substrate of soils, the xeric fennel soils. They are very, very poor. So that is very interesting. And a lot of research is going into them. Into the why and how can we maybe how can we understand this and maybe make an amendment to soil that can create these soils. And if we understand it fully and we can repeat this process, then we can make the soils of Australia, of Africa, parts of Brazil, we can make them fertile. Okay, so that's the terra preta. Those are pretic anthrosols. Sorry? Okay. We have also in the Netherlands, we like to dig in our landscapes and recreate and create landscapes. And we have many examples of man-influenced or even man-made soils. Here you see a peat dike, which is a dike in a peatland polder. And you see here the original peat, just original peat. And then above it, you see dredge material brought on to heighten and make the dike functional. And you see all kind of artifacts. That's technic material, man-made material. And you see that as we go up, it's also soil as an archive, as a function of archive, remnants from the 17th century, remnants from the 18th century, and glass higher up in the profile when glass was more affordable in households. So it's also an archive through time. It's a kind of archaeological archive. So this is a technosol because there's technic material, brought on material. So we already have in WRB 2 separate units that are man-made, and that is favorable because in many soil maps, the cities are white spots on the map, as if there is no soil there. But of course, there are soils there. And in the WRB, we can give them a name. In the USDA soil taxonomy, they are going to have an anthropogenic class as well, the anthrosols, they are going to call them. And or enteric soils, I think. Well, anyway, they are going to identify a specific order for the man-made soils, which is good, I think, because we also need to map the urban soils and the mine spills and other type of soils. And here you see, and that's the other thing I wanted to say, that we use these qualifiers in WRB to characterize the soil conditions that we find at a particular spot. And here you see an urban soil. So we see the original heathland soil here, which is a potsoil. Then we see the remnants of a garbage heap. And then we see construction sand for the building of houses. And then the pavement to close the soil. And so that is a real urban soil. We have artifacts here. And in WRB, we call that soil, it's a I don't know if the order is right, but it's an urban garbic ecranic technosol. And that is all quite exotic in terminology, but garbic is of course from, it contains garbage remains. Ecranic means sealed, so it's a sealed soil. And urbic is from city soil. So exotic names, but ultimately you can quite specifically name a soil, and by the name you can understand that the soil has such a buildup. Okay, now let's have a look at the climate wall. Because I would like to show you other parts of the museum as well. Here, the climate wall, if you look from left to right, you see quite a range of variation. And we can judge that mostly by the color. If you look from left to right, we have the humid tropics. These are arbitrary climate zones that we made. You have the desert, the hyper-arid zones. We have the temperate area, subtropics, and there are different soils there. And then we have the steppe areas and the subarctic. And looking from left to right, we see this color gradation. We have orange and red colors on the left. We have white spots in the profile in the deserts. We have different sets of colors in the temperate area subtropics because there are different processes dominating there. And then we get brown colors, accumulation of organic matter in the steppe area and the subarctic area. And that points to specific processes dominating in different climates. So in the cold areas, there's buildup of organic matter because there's little breakdown. In the steppe area, something similar. There's high biomass development, high bioturbation, rich substrate, and then you get this super A horizons. And also there is a harsh winter, which conserves all the material, and then the organic matter pump starts again in the spring. So you see that specific soil forming process dominate within climate zones. And the same in the desert, there is buildup of salts because the dominant movement of the little water that falls annually into the system is upward. So the diluted salts will travel upward with the evaporating water. The water will escape to the atmosphere and the salts will remain in the top. And then in the tropics, you have extreme leaching. So all parts of this Earth's surface, but also extreme climate, high rainfall, high temperature, which accelerates the soil processes and also accelerates leaching. And therefore you get these reddish and yellowish profiles with the dominance of iron and aluminum, oxides and hydroxides, and gypsite and hematite. Because much of the other components have left the system, as silica and other components have been leached out, and iron and aluminum relatively accumulate, relatively because it was already there, but it accumulates because other components have leached out. Now, if we look at the steppe soil, that's a wonderful soil. Ukraine is a lot in the news nowadays, but they are also known for these beautiful steppe soils. And yeah, they have an enormous A horizon, 1 meter thick, beautiful structure. Other beautiful features like fertility. You see the secondary carbonates in the lower part, which are diagnostic for chernozems, by the way. They have to have them to be classified as a chernozem. And these soils form under this steppe climate, which is rather dry, in 200 millimeter to 450 millimeter. I've seen them in Romania under 600 millimeter, but usually they are a bit drier, which means these are beautiful soils, but they are in a rather dry climate for agriculture. So sometimes farmers suffer from dry years or supplementary irrigation is needed. Now, even though these are beautiful and fertile soils, they are also vulnerable to degradation, and they are degrading worldwide because man is plowing them. We are plowing them. They are used for farming, and the danger of that is that you destroy the structure, and then in these rather dry climates, you get wind erosion, and then topsoil is moved to other parts. And in the United States, there has been historic recording of the Dust Bowl in the early 20th century, where the prairie soils were plowed and then massive erosion took place. People couldn't see the sun anymore because of the sediment load in the sky, and well, it caused famine and other problems. And zero tillage was one of the responses. That doesn't say that everybody practiced it, but zero tillage is one of the ways to overcome this particular management issues on these particular soils. Good. So we continue through the other climates. Let's have a look at the Louvi soils, because we talked about podsoilization, different soils formed under different specific processes. And you see, other thing I would like to mention is you see the very discrete boundaries that you have here in the soil. And these are very sharp horizon boundaries, and each horizon has very particular properties. So I know in digital soil mapping, you make splines and you try to model the depth function of soils, but one of the soils that doesn't work well is this pot soil, for instance. And in many soils, they do have sharp boundaries, both in the spatial content as in the depth component. Some soils are gradual in terms of how they vary over the landscape, for instance, but some soils are not. Like glaze soils, they can have a very sharp boundary with other landscape components. And glaze soils are poorly drained soils. And also these pot soils, they have beautiful appearance of a very distinct genetic horizons. And these genetic horizons are then identified by codes, and these codes are also used in grouping or separating soils in the classification system. Another soil forming process, I have to speed up because I see time is running out, is clay illuviation, clay movement. And you see here a beautiful soil from Greece, and that's a very general soil process where clay moves over time, long time periods, and accumulates in the subsoil. And you get these beautiful structural elements here, angular blocking, wonderful pores here, micropores, and these soils have a good store for nutrients and water in the subsoil. And fertile soils and rich clays, because the clay has a high buffering capacity and high base saturation. So wonderful soils for agriculture. Now, the saline soils I already discussed. There are different saline soils distinguished in the WRB system. Sodium saturated soils, sodium fluoride saturated soils. We also have gypsic soils, so gypsy soils with calcium sulfate, and calcium carbonate rich soils, so calci soils. And these soils are used a lot for agriculture, be it with specific management limitations, but calci soils are used quite a lot for grain production in Jordan, in Spain, around the Mediterranean. Yeah, and then these soils, if you think about generalizing information of soils, these soils are also a headache, because these phenol soils or oxysoils in the American classification, they can be clay rich, but they function as a sand often, because there's high aggregation of the smaller particles into larger particles. So because of the iron, and the iron sticks them together, and they feel even as sand in the field, but actually they are clay rich. And also they are a bit different than other soils in the collection in the world. They have a near neutral charge in many cases. So which means most soils have a negative charge, and the cation exchange capacity, but these soils are nearly neutral, very low exchange capacity. And organic matter is, of course, this particular soil, by the way, is quite high in organic matter, but it's masked by the redness of the oxides, of the iron oxides. So very particular soil for management. Burning is one of the ways to increase the fertility of these soils if you have no agricultural inputs, slash and burn. And organic matter management is obviously also important. If you have management inputs, then you can fertilize, do liming. They're also very phosphate fixating. The iron components will fix the phosphate to the extent that plants cannot access them. But then, well, if you have inputs, then you can overcome these limitations. Many people do not have these inputs in tropical areas, like for instance here, these yellowish soils from the heart of Borneo. And when you don't have that, and if slash and burn is not possible anymore because there are too many people in the area, so you cannot let the soil regenerate, which it requires after 2 years of farming, then you have to work with the conditions as they are. And then you select, for instance, crops that that can withstand the acidity of the subsoil. So acid tolerant or low nutrient demanding crops like cassava, pineapple, rubber, black pepper, those kind of crops. And you see that, of course, often in these areas that such kind of crops are grown for people that have no other options. Now we have soils, poorly drained soils, like clay soils with loose clay particles all over the soil, and then with structure formation in the top where there's actually oxygen access. In the sloping lands, we have mostly shallow soil, so erosion is the dominant feature, like in this soil, only a shallow topsoil, and then parent material high up in the profile. Now, here you see a soil which is mostly rock, and only a few centimeters of soil on top of it in the degrading rock. And in WRB, we do not classify the soil by the depth part of the soil is already identified. It says the first 2 meters of the earth crust, wherever it occurs, unless there's more than 2 meters of ice or water column on it. So even bare rock, even city soils are all classified with a specific name. And this rock, for instance, how do we classify it in WRB? It's the class of the leptosols. Leptosols are the class of the shallow soils. You see it, leptosols. And but then they are called nudilithic leptosols. Nudi from bare, lithic from rock, and leptosols from shallow soils. Okay, I'm nicely within time. I would like to show you the volcanic soils. They are quite particular soils with particular stories, particular properties. This soil here, we have secondary schools coming into the museum, and they. Oh, I will turn the camera around. Yes, let me first tell you the story. We have secondary schools coming into the museum, and we tell them about what is soil, what is the importance of soil, and then they will go around, be it primary or secondary school, more or less the same, but with different level of complexity. And then we ask them, look for a soil and draw it, or maybe write something about it, what you can say. And then the geography teacher sends me a report of the students. And once the students wrote in one of those reports, I saw a Mr. Trump soil, and I thought, well, not everybody is interested to follow the class and just write up something. But then a few weeks later, I gave a tour in the museum, and then I saw this soil. And well, you can imagine that I had to laugh, because I could ultimately understand, it's the soil on the right, obviously, why the remark was made as it was. So it's the soil from Namibia, which was called Nambia by the previous president, by the way. And well, anyway, it's a Rubik Areno soil, but jokingly we call this the Mr. Trump soil. We have here 3 volcanic soils. Volcanic soils can be very different. Why? Because of the chemical composition, because of the age, and because volcanic soils just start off as rubble, as ashes, and then they are not volcanic soils at that moment in time. They develop into volcanic soils, and if they get older, they will go out of that group again and maybe develop into feral soils or oxo soils. But volcanic soils develop from volcanic ashes, volcanic material, and they can be very varied. And we think that volcanic soils are fertile, because you see people in the tropics going up to the slopes, up to the crater, doing agriculture, because the conditions of the soil are favorable. But also you go up, if you go up in the tropics, with going higher up, you get a cooler climate, which means you can grow different crops like strawberries or potatoes. But also because the soil fertility, because the volcano brings ashes into the landscape, rejuvenating the soils, and therewith fertilizing the landscape. Yet, I always ask the question to students, are all volcanic soils fertile, equally fertile? Well, if you ask the question that way, you can already understand that the answer to the question is no. And why is that? That is also because of the nature of the ashes, the nature of the volcanoes. And I always explain that by the geography of Indonesia and the population distribution. This soil is from Indonesia, from Lake Toba, north of Sumatra. It's a very big lake and a very big remains of a crater, because in Sumatra the volcanoes are acid, and they tend to, the magma tends to block the volcano outlet, and then pressure builds up and they explode. But they bring low weatherable minerals with the ashes into the landscape, meaning poorer soils. And if you go to Java, where the population pressure already for thousands of years has been high, with high cultural development, agricultural development, there the volcanoes are intermediate, andesites. And if you go to Bali, the volcanoes are dominantly basic and bring more weatherable minerals into the landscapes, more fertile soils, 3 rice harvests in a year. In Sumatra, up to 100 years ago, was rainforest, and now still lowly populated. So that's an illustration of volcanic soils and their fertility. Now, the time is over. That doesn't give me the chance to tell you about the Icelandic soil, which is a nice story related to the French Revolution. But well, maybe there's I can tell you that next time. You see here at least peat intermixed with ash layers. It's yeah, okay. Let me stop here, because I see the time is out and I don't want to keep you longer than is planned, because you also need your break. The museum is also available online. We have an online presence of the museum. You can walk with a Google tour through the museum from your computer. And also there are access paths, virtual access to the collection, not only what you have in the museum, by 2 ways. There's a world map where you see the profiles represented on the place where they were sampled. You can click the profile for the information. And there's a collection searcher. You can collect on the soils that we have for a country and or for the soil type. And then you get a selection from our collection. You can see the high resolution image and the database file. So you can always go back to the museum online. And if you're in Wageningen, of course, you are warmly invited to visit us in the museum as well, where I would like, or my colleagues and I would like to meet with you. I will give the chance for the people that do not yearn to go to to the bathroom or have a coffee to still ask a question, and I would like to give the possibility now. Anyone with a question?
I see applauses.
Well, if there's no questions, also fine.
Yeah.
We can take a break.
Stefan, thank you very much. But there was one question about how we make the monoliths.
Yes.
And maybe it's, yeah, we don't have much time to answer that question, but maybe
I can do it briefly, Maria.
okay. Yeah, please.
Okay, thank you. Got to include that in my story. So what we do on every site that we collect a monolith from, we completely describe the environment, the slope, the altitude, the vegetation, the land use, and then we look into the pit of about 2 by 2 meter, and then describe the wall according to the parameters that we can describe and observe. And then we sample each of the genetic layers, about 1 or 2 kilogram of material, and then we dig out a column. So we dig out a column of, let's say, 25 centimeter width. We push a box over it and cut the column from the rear side. And then we we take the box out of when the column is loosened, we take the box out of the pit, we close the lid, we send it here to Wageningen, and then we add a glue to it, a transparent glue. We saturate that column with glue for about half of the volume. We glue a board on it, and then when that is hardened and fixed, we turn it around, take the sides off, take a bit of material from the other side of the soil column, and then we have a soil that we can sustain for a long time and also show it on the wall. And then the samples are sent to the laboratory and into the database together with the description, and well, and we can show the profile here on the wall.
Thanks, Stefan. So is there any other question? I don't see any hand. So
okay, well then, thanks for attending, and enjoy your break and the last part of the program.
thanks, Stefan. But before you go for the break, it's time. So we give you a lot of information during this week, but now it's your turn to give us some feedback about the course. So I'm going to share with you a link to the evaluation form that we do each year, because for us it's very important to have the feedback each year. And then we have a look with all the teachers and with the team, and then we try to improve the next time. So I will be posting this form into the general channel. Just follow it, take your time to fill it in. And you have enough time because it's 10 to 3. And then we will only start with David Rossiter's lecture at 3:15. So thank you very much, and please give the feedback because it's important for us. And Emily, I think you can stop the video recording.